We will now rewrite this given logarithm as a single logarithm. I'm going to use this product rule to write this as a single logarithm. So we have these two laws. That is, the first one says the sum of the logarithm of numbers equals logarithm of the product of those numbers. So if we have logarithm of m added with the logarithm of n and then added with the logarithm of p, it equals logarithm of the product of those numbers. That is, product is m n p, and then we take this logarithm. So first I'm going to apply this to this logarithm, and to apply these two laws we have to consider that the bases are the same. So that should be the first step that we should follow. Clearly we can see that the base is a everywhere. That is, when I try to combine these three logarithms, I can clearly see that the base of all the three logarithms is a. So we can use the logarithm rule. So when we combine these three logarithms, it becomes logarithm of product of those numbers. That is, we have the numbers as x, 9 and x squared plus 1. So these three will get multiplied. So I can do it here. That is x times of 9 times of x squared plus 1. So this we can write down this as 9x times of x squared plus 1. So I'm going to put 9x times of x squared plus 1 as a product, and the base is the a. So this is our first step, and then we have this minus log of 7 to the base a. Now we can apply the quotient logarithm rule, which says that logarithm of m minus logarithm of n equals logarithm of m over n. This basically tells us that if we find the logarithm of quotient of numbers equals logarithm of the difference of the numbers. So we can now combine using this quotient law. So I'm going to combine this. So whenever we have the subtraction, that number will get divided. So this can be rewritten as logarithm of, we have this numerator part as 9x times of x squared plus 1 over the 7 will get to the denominator, and we put the same base, that is a. So this is the, we can in fact put a bracket, just remove this. So this is the single logarithm of the given logarithmic expression. Let's solve this equation. So we are given the equation in terms of exponent. We have e raised to the power of x squared equals e raised to the power of 3x times 1 over e raised to the power of 2. So first I'm going to simplify this right side expression using the exponent law. A raised to the power of m over a raised to the power of n equals a raised to the power of m minus n. So basically we can see that the bases are same. That is, we have e in the numerator as well as e in the denominator. These two bases are same, which means we can apply this division law, and when we do that the powers will get subtracted. So I can combine these two exponents as a single exponent as 3x minus 2. On the left side we still have this e raised to the power of x squared. Now we can clearly see that this is an equality involving just one exponential expression on both sides. So we just have e raised to the power of x squared equals e raised to the power of 3x minus 2, and there are no numbers getting added or divided with this expression, which means the bases are same. We have the base as e over here, and here also we have the base as e. So when the bases are equal, the powers will also be equal. The powers is x squared here, and the power over here is 3x minus 2. So we can simply rewrite this as x squared equals 3x minus 2. Now let's subtract 3x and add plus 2. So therefore we will get a quadratic equation like this: x squared minus of 3x plus 2 equals 0. We can solve this either by using quadratic formula or by factoring. I'm going to use the factoring. So we see that the product of two numbers should give 2, and the sum of two numbers should give negative 3. So let's think of those two numbers. Probably we can have negative 2 and negative 1. When you multiply these two, we get positive 2. And when you add these two, we get negative 3. So we have it as negative 3. So therefore, this could be factorized as x minus 2 times of x minus 1 equals 0. And this gives the solution as either x minus 2 equals 0 or x minus 1 equal 0. And this implies we can solve for x from both equation. So from the first equation we get x equals 12, x equal to 2, and from the second equation we get x equal to 1. So these are basically the solutions. However, let's go ahead and check if this satisfied the given equation. We will now check both solutions by substituting them into the original equation and verify if they satisfy the equation. So I'm going to substitute x equal to 2 first into this equation. I'm going to replace x by 2. So therefore the left side expression will become e raised to the power of 2 squared. And on the right side we have e raised to the power of 3 times of 2 divided by 1 over e squared. So on the left side we have 2 squared is 4, so we will have e raised to the power of 4 equals e raised to the power of 6 multiplied by 1 over e squared. And we can simply cancel these powers, or we can simply subtract them. So when we do the subtraction, 6 minus 2 gives 4. So we end up with e raised to the power of 4 equals e raised to the power of 4, and this is true. And this means the solution x equal to 2 is correct. Now let's substitute x equal to 1. So let me clear this up. And when I do that, I will be getting e raised to the power of 1 squared on the left side. And on the right side, I get e raised to the power of x is replaced by 1. So it becomes 3 times of 1 over 1 over e raised to the power of 2, or it's just e squared. So on the left side, we get 1 squared is 1. So e raised to the power of 1 is basically e. And this gives on the right side, we have e raised to the power of 3 divided by e raised to the power of 2. We can subtract the power since it is a division of the exponents. So 3 minus 2 gives 1. So this is equivalent to e raised to the power of 1 or equal to e. So we get the relation or the equation as e equals e, and this is also true, which means x equal to 1 is also the solution of this equation. Let's evaluate this logarithm expression, that is we have log 15 to the base 0.5. We can use this change of base rule. This says log a to the base b equals log a to the base c divided by log b to the base c. And here c is another number. We can choose c as any number that we prefer. Usually we choose c as either 10 or, I'm sorry for that, you can choose this as e. So I'm going to rewrite this using the change of base rule. That means I can rewrite this as a log of a is 15 over log of b is 0.5, and I'm choosing this logarithm as base 10. I can either write down, or this could be simply written without the log base 10. So we can simply rewrite this as log 15 over log of 0.5. And it's quite understood that if we write like this, it refers to log to the base 10. Now we plug this into the calculator, and when we do that, we are getting the value of negative 3.906 approximately to 3 decimal places. So this is the value of the given logarithm using the change of base rule.